Hey guys, in this video we'll begin discussing gas laws, the first law being Boyle's law. But let's look at what we know so far about gases. Okay. So in the last couple PowerPoints we've talked a lot about kinetic molecular theory. Right? That's our theory that all the matter around us is made of really tiny particles, and when they are in the gas form, that means that those particles have a lot of energy. They're moving around very quickly. Their intermolecular forces can't hold them down like we see in solids and liquids. Okay, so we know that our particles are moving really, really fast. So there's some factors that affect these particles. One of them is pressure. We learned that atmospheres is the unit we're going to use for pressure. The abbreviation is ATM. Another factor that affects it is volume. We measure that in liters. Temperature, which we measure in Kelvin, so something we've never really used before. I don't know if you've used that in other science classes, but typically other classes use Celsius. We go all the way to Kelvin, the reason being that we can't have negative temperatures in Kelvin. So our equations aren't affected by any negative possible outcomes. And our last factor that affects gases is the amount, so the actual amount of particles that are there, and we measure that in moles. Okay, so before we get on to our first gas law, I just want to talk briefly about equations. If you've seen in the PowerPoint I posted, I go into more detail about this, but equations to me are one of the cool parts of science. It is awesome how we are able to explain the natural world with these equations. And I absolutely get it. You hear equation, you think math, and you think this is going to be really bad, and it's going to be confusing, it's going to be hard. I know they're hard at first, but if you give them time and you get experience with them, they're actually there to make your life easier. Right? It's not us making equations to fit the natural world. The natural world operates by these equations, right? It's the example I use in the PowerPoint is that we're revealing Mother Nature's tricks there. So it's really how the world already works. We're kind of figuring out how that works and making a useful equation out of it. So they're tools for us to make really cool things. Okay, so enough of that. Let's get on to our first gas law, Boyle's law. So we know we have all these different factors that are going to affect our gas as we investigate it a little more. In Boyle's law, we're not looking at all of these factors at once. We're only going to look at pressure and volume. Okay, so these two. Our other two factors are going to remain constant. So these do not change. These will stay the same. It's something I didn't say in the PowerPoint for you guys. Okay, these do not change. So only pressure and volume are going to change. Temperature stays the same the whole time. The amount of particles stays the same the whole time. Okay, so like I just said, it focuses on just pressure and volume. So where this law came from was a guy named Robert Boyle. He did a ton of experiments with gases, looking at pressure and volume, and he figured out this equation. Right? He kept getting the same result over and over again, that pressure and volume are inversely proportional. So this equation describes that phenomenon. When pressure goes up, volume goes down. If pressure goes down, volume goes up. So that is what this equation shows us. I know it's kind of hard to see that. You guys aren't too familiar with equations, but we'll get some practice with that. Okay, so here is Boyle's law. What these things mean, P1 and V1 are the initial pressure and volume. They are the start pressure and volume that you have before anything changes in your problem. P2 and V2 are the final pressure and volume, so it's the end, it's what happens after the change. Right? When we have equations like this, only one of these is going to be missing. Right? We can't do a problem where we have two missing, and there's no need to do a problem if we have all of them. So there will be one that is not given to you in the problem, and you have to plug all these values into the equation to find that missing one. Okay, so here is our example. A balloon on top of a mountain has a pressure of 0.5 atmospheres and a volume of 10 liters. If the balloon is brought to the beach where the pressure is 1 atmosphere, what is its new volume? Okay, so balloon on top of the mountain, when it comes down from being really high up, the air pressure is going to change, and we want to know what the new volume of the balloon is. Okay. When we do these problems, first thing you should always do is take all your variables that you have in the equation and just list them down the side. All right, we want to see which ones we have. Before you do any math, we're just looking at what we have. Okay, so initial pressure at the start of this, right? We know we're looking at the balloon's pressure. What does it have at the beginning before it changes? So at the beginning, it's on top of the mountain. It has a pressure of 0.5 atmospheres. So plug that in right there. V1, when it's on top of the mountain at the beginning, we do know its volume. It has 10 liters. Okay. Then it changes. It's brought down to the beach. The atmosphere is going to change, right? Or the pressure changes to 1 atmosphere. So we know when it changes, it becomes 1 atmosphere. But we do not know the volume. It is asking us what the volume is. So that is our question mark. But we do know that the unit is going to be liters, right? So we're blank liters. That's what we're looking for. So we just take these and plug them into the equation now. P1 is 0.5. We use our units so we can check our answer at the end. Volume 1 is 10 liters. That's the left side of our equation. And the right side, we know that P2 is 1 ATM. And we do not know how many liters. Okay, this is where we do our algebra. Okay, so we want to get liters by itself here. So we're going to divide 1 atmosphere over. So 1 ATM divided on both sides. And that makes this really easy because when we divide by 1, it doesn't really change our answer. We have 0.5 times 10. Hopefully you can do that in your head. It is going to be 5. And look at our units now. Atmosphere times liter divided by 1 atmosphere. The cool thing about using our units like this is it helps us see that we have the right answer. If you notice, ATM divided by ATM is going to cancel out. 5 divided by 1 is just 5. So we have 5 liters is our mystery amount of liters. That is our answer. V2 equals 5 liters in this problem. Okay, so that's one where we're missing volume 2. Let's look at this next problem where we're missing pressure. All right, so in this problem, a balloon on Earth has a volume of 15 liters when it's at a pressure of 2 atmospheres. If we take that same balloon, it would expand to 5,000 liters if it was on Mars. So what is the pressure on Mars if our balloon goes from 15 liters to 5,000 liters? Again, list out what you have. P1, V1, P2, V2. Our initial conditions is when the balloon is on Earth. So it's volume, V1, 15 liters, at a pressure of 2 atmospheres. These two things go together. They're both the initial conditions. So 2 ATM, 15 liters. Now the balloon changes. It goes to Mars, on Mars, 5,000 liters, right? Doesn't say volume around it. Doesn't specifically tell you that, but you know it because of the unit here. So its volume is 5,000 liters. And it wants to know what the pressure is. So that is our missing variable, but we do know it is ATM, right? Pressure is always in atmospheres when we do these problems. If it's not, we would have to convert it, but we're not going to get there. Okay, so we have all our variables except one. We can plug them into the equation and now solve. So P1 is 2 atmospheres. V1 is 15 liters. That equals, we don't know what P2 is. And V2 is 5,000 liters. Okay, so we know this is going to be 30 atmospheres times liters on this side. This side is going to be, we don't know the ATMs, times 5,000 liters. We're going to end up dividing by 5,000 liters on this side to cancel these out. We divide by 5,000 on this side. Okay, so we see that liters also cancels out. We only have ATM left as our unit. That's our pressure that we want. When you do 30 divided by 5,000, you'll see in your calculator you get 0.006 ATMs, and that is our missing atmospheres. So we know right here that P2 equals 0.006 atmospheres. So that is the pressure on Mars. Okay guys, hopefully this helps. If you have questions, send me some emails. See ya.